Flore. Okay. And after a postdoctoral appointment at the Max Planck Institute of Quantum Optics, she has become a junior leader at the Max Planck Institute for Science of Light. Okay, Flore, the stage is yours and we will enjoy the talk.
Yes, thank you so much, Dimitri, for the kind introduction, and also thank you all of you for the invitation for me to speak on this platform about my work. So as mentioned, my name is Flore Kunst, and I'm a research group leader at the Max Planck Institute for the Science of Light in Erlangen in Germany. And Erlangen is this very small village right next to Nuremberg, which is where I'm sitting right now behind my desk at home. And I will be talking to you about exceptional non-Hermitian topology. So here on the first slide, I already have an example of what non-Hermitian topology could look like. So what I put up here is a very sort of easy example of a non-Hermitian Chern insulator, where I put the situation under periodic boundary conditions here in gray. So you see there are bandgap closings, but under open boundary conditions here in blue, where you see this edge state appearing here. And you see that these spectra are vastly different. And this is already a very significant feature of non-Hermitian topological systems. Namely, this indicates a breakdown of the bulk boundary correspondence. And I'll get back to this later on. Right, so non-Hermitian topology, what do? We study topological phenomena in non-Hermitian systems, which means that we assume a Hamiltonian, say, or any other type of operator, or maybe I should better say matrix, that describes your system that is non-Hermitian, so it's not equal to its adjoint. And what we do then is actually look at the properties of these matrices, and it turns out that this has beautiful mathematical properties that can be seen in real-world experiments. For example, here you have a single photon interferometry experiment where you can see so-called exceptional rings. And this is a truly non-Hermitian feature, which I'll explain to you in a few slides what they are exactly. So one should think of these non-Hermitian operators or non-Hermitian matrices as an effective approach to describe systems with dissipation. And they have many applications, particularly in classical systems. For example, they appear in mechanical metamaterials, they govern electrical circuits, but also optical metamaterials. And this is also why I'm at the Max Planck Institute for the Science of Light. So non-Hermiticity appears in many, many optical systems, because when you have photons, you always have loss. So here I put up an example, for example, of an optical waveguide lattice where the wiggly waveguides are lossy. And this is governed by a paractual equation, which looks like a Schrödinger equation. And because of the lossy waveguides, you then have an effective non-Hermitian Hamiltonian. However, these non-Hermitian operators also have merit in quantum systems. If you think, for example, of a system that is weakly coupled to a Markovian bath, then this is captured by a Lindblad master equation, as is shown here. And you can rewrite this equation in this form, where you have an H effective here, which, as you can see by construction, is non-Hermitian. Such that in the short time limit, when this quantum jump term here does not take effect, your dynamics are actually governed by this non-Hermitian effective Hamiltonian. Note, however, that if you look at the full equation and you write it in this form, this Liouville matrix here is also a non-Hermitian matrix. Another place where you can see such a non-Hermitian effective Hamiltonians would be if you look at material junctions in quantum transport. Here you get self-corrections from the leads, giving an anti-Hermitian self-energy. Similarly, if you look at finite quasi-particle lifetimes due to, for example, electron-electron interactions or electron-phonon interactions, etc., you also get self-energy corrections to your single particle effective Hamiltonian in the system, which render the Hamiltonian non-Hermitian. And if you're interested in this field, I'd like to refer you to a review paper that we wrote on this topic about 2 years ago. But before I dive into all the physics and all the interesting aspects here, I would first like to introduce you to some basics of non-Hermitian matrices, to introduce the field and to already show you that in this very simple 2x2 matrix I've written here, you can already find very rich physics. So this matrix is now non-Hermitian because we will explicitly assume this alpha to be not equal to 1. The eigenvalues of this matrix are generally complex, as you can easily see. You get the square plus minus square root of this parameter alpha, where we then associate the imaginary part of the eigenvalues with a lifetime. And you can think of this alpha, square root of alpha, spanning a Riemann surface with a branch cut and a branch point. So here you see schematic of this square root. If you then compute the eigenvectors of this 2x2 system, you see that they're non-orthogonal. So psi r plus and psi r minus are not orthogonal to each other. Moreover, you see that the left and right eigenvectors are inequivalent. So if I take the dagger of the right eigenvectors, which normally gives me the left eigenvectors, you see you get something else here. However, you can remedy this situation, if you will, by taking a orthogonal set as long as alpha is non-zero. So you can take the inner product between the left and the right and normalize those. And this then gives you what is known as orthogonal quantum mechanics. So let's write this a little bit more formally. So what you do is you have your Hamiltonian, it has a right eigenstate with energy E. Then it also has a left eigenstate with energy E. And for a non-Hermitian system, you can then show that if you take the dagger of this, that the left eigenstate of H is actually the right eigenstate of H dagger with E star. And of course, if your system is fully Hermitian, then you immediately see that this H dagger becomes H, E star is E, and you see if you take the dagger or the adjoint of the side of the ULs, you get the URs as expected. So these are not orthogonal, however, away from, but are arbitrarily close to exceptional points. And here you have that word again, and I'll get back to that on the next slide. You can obtain a complete orthonormal eigenbasis when you normalize in this way. So you take the left guys and the right guys, and you take the inner product between them. And this is fully consistent with the fact that to find the eigenvalues here, you need to take the so-called biorthogonal inner product of your Hamiltonian operator in this way. Right, so what are now these exceptional points, right? This alpha 0, if you will. So you see that the system is doubly degenerate when alpha 0. Now, this 2x2 matrix becomes a Jordan block. And only one eigenvector remains. So instead of having two right eigenvectors, now I only have one eigenvector. And this is the signature of an exceptional point. So one says the Hamiltonian, or more precisely, the non-Hermitian matrix is defective at these points, which means that the geometric multiplicity is smaller than the algebraic multiplicity. In other words, the number of linearly independent eigenvectors is smaller than the root of your characteristic polynomial, which sets the algebraic multiplicity. So here I have an exceptional point of order 2 because two eigenvectors coalesced onto one and two eigenvalues are degenerate. And this, as I said, is called an exceptional point, and here's a nice review paper about these points, although it's a bit older. Now, if you encircle an exceptional point, something very interesting happens. So if I now write the argument of this alpha, and I then go encircle, so I added 2 pi, so I go around this exceptional point, you see that the square root of alpha goes to minus the square root of alpha. So I have flipped the eigenvalues, but I've also flipped the eigenstates. So I start in one eigenstate, I go around once, I end up in the other eigenstate. This is a truly non-Hermitian effect associated with the exceptional point, and it means that you have to actually go around twice to end up at the point where you started. And this is a manifestation of the double Riemann-Sheet topology. Okay, so now we have seen a very simple example, which holds something that you see in more or less all non-Hermitian systems, namely exceptional points. So let's now ask ourselves the question, when do these points appear? So let's take a step back and actually first start with the question, when do two bands cross in Hermitian systems? And it's quite easy to see that for two bands to cross in a Hermitian system, one needs to satisfy 3 constraints. And you can see that from the following equation. So any 2x2 matrix can be written in terms of the polymatrices. So this sigma here is the vector of polymatrices. And note that I've set the identity term to 0 here, because the only thing it would do is shift around my eigenvalues, but it wouldn't actually say anything about the degeneracies. So if you then write the eigenvalues of this equation here, where you have this d vector which has 3 components, you see that you find the following. So to find the degeneracy, meaning that E plus needs to equal to E minus, each 3 of these guys here need to be set to 0, which gives you 3 constraints. And the simplest example where you can see such a stable 2-band crossing that you cannot gap out is a 3-dimensional Weil cone in a Weil semi-metal, which has the k dot sigma dispersion. So let's now look at non-Hermitian systems and ask, okay, how many constraints do I have there? In which case I can find a 2-band crossing. And even though you have many more parameters because your system is now non-Hermitian, it actually turns out you only need to satisfy 2 constraints. So the codimension is smaller. So again, let's use the same argument as for the Hermitian case to explain how this comes about. So we still have this d dot sigma form, but now this system is non-Hermitian, which means this d here has a real part and an imaginary part. If I then write the eigenvalue equation, this is what it looks like. So to find a degeneracy here, I need to set these two terms here to 0, meaning that I only have two constraints, namely the magnitude of this dr and this di need to be equal, and the r and di need to be orthogonal to each other. And if I satisfy these constraints, I find an exceptional point. And these exceptional points also have very interesting properties. So, of course, the fact that you only have two constraints also means that they're extremely abundant in non-Hermitian systems. You actually have to work quite hard not to find any. So these exceptional points, they always come in pairs and they're connected via Fermi arcs. And this can again be understood from this set of equations here. So these two equations can be satisfied on some closed curve in some two-dimensional parameter space. So let's assume that this black curve is the curve on which this magnitude condition is satisfied, and this green curve is the curve on which this dot product is satisfied. If I'm now on this green curve here, where this part is 0, and I'm in this region here, where the difference between these magnitudes is negative, then you can immediately see that the term under the square root becomes negative, i.e. the real part of this E is 0. So this light green curve actually corresponds to an open arc in your spectrum. And this is known as a Fermi arc in the literature. And you similarly also have such an arc in the imaginary part. And actually skipped one step, because if you have these two curves, then very obviously when they overlap, you have, at the points where they overlap, you find the exceptional points, and very obviously you have a pair here. And note that in the very special situation where they just touch, this is no longer an exceptional point. This becomes an ordinary degeneracy, where the two exceptional points merge. Okay. Another interesting feature, which is very much related also to the example that I showed before, and also to the fact that you need to wind twice, is that the dispersion of these exceptional points are non-analytical. So instead of having a linear dispersion like the wild cone, they have a square root dispersion. Okay. So what now? Yes, please.
Could I interrupt you?
Yes, please, go ahead.
If I understand correctly, then when you go around the wild point, your spinner takes a phase pi. But you have mentioned that when you go around the special point, you have a phase, the phase that is generated is equal to 2 pi.
Okay, so this is not exactly what I'm doing. So let me get back here. So here I'm going around by just saying, okay, I'm going around by varying this argument of alpha by 2 pi. And of course, if you go around the wild point, you would also take going around with 2 pi. If you go around, of course, then you pick up this geometric phase, if you will, right? This pi factor. But what I'm describing here is really, if I start at the point here, say in this purple, and I go around, then I actually end up here in this green sheet and not again here, which is very different for the wild point, right? If I start here and I go around, I'm here. And this is because in the non-Hermitian case, you can define an adiabatic theorem quite well, but you cannot do this actually in non-Hermitian system. These are always non-adiabatic. So that is what this refers to.
Okay, thank you.
Yeah. Right, so these exceptional points, they can be seen in experiments. So this is not just some mathematics, and I already showed you something in the beginning. So these Fermi arcs that I just described, they've been observed in a photonic crystal where you have losses in the system. And here you see the experimental results versus the simulation results, and you really see these open arcs appearing. Also, this square root dispersion that I mentioned has been associated with an enhanced sensitivity against perturbations. So here you have microwave cavities where in the top row, they operate at a diabolic point. So you have this linear dispersion, but in the bottom, they introduce the tips here where they introduce loss and then engineer it such that it operates at an exceptional point. And indeed, you see here square root dispersion. And the idea is then, if you disturb this a little bit, that the system operating at the EP is much more sensitive because it has the square root dispersion, and indeed you see a much wider transmission. Another place where you can find such as EPs is, for example, in Bragg's categories, where they made them PT symmetric, where PT refers to parity time, and I'll get back to that in a few slides, where they, for example, observed a unidirectional invisibility. So these exceptional points, they can really be seen in experiment and also be harnessed for applications. Right. So now the question that we're wondering about, what happens if you add symmetries into the game? We know that symmetries can stabilize Hermitian degeneracies. How does it work for non-Hermitian degeneracies? So in Hermitian systems, one has 10 symmetry classes, and they were described in 1997 by Atlant and Simbauer. Now let me write them first. So these are the symmetries that you have in Hermitian systems. And you note here that I've already split them, anticipating that we're going to do non-Hermitian things. But in principle, you have particle symmetry, time reversal symmetry, and chiral symmetry, and then combinations of those gives you the 10 symmetry classes. Now, in non-Hermitian systems, it turns out you have 38 symmetry classes. And the reason why there are so many more, and I put arrows here, which symmetry classes are in this classification described in these two beautiful papers, is exactly because non-Hermiticity gives you the following effect, namely, if you take a transpose of your matrix, it no longer equals complex conjugation. So you get two flavors of particle whole and of time reversal symmetry. Moreover, H is no longer equal to H dagger, so chiral symmetry can also now be split into symmetries, and you can introduce a new symmetry known as pseudo-Hermiticity. And let's focus on this symmetry here to understand how the presence of certain symmetries actually affects the appearance of EPs. So this is again the pseudo-Hermitian symmetry. This is what it looks like. And let's again look at our generic two-band model. So here I again introduced this d dot sigma, but now I've reintroduced the identity. So sigma naught is the 2x2 identity for generality's sake. If we now want to satisfy the symmetry, we can basically make two choices for the sigma. Either we make it identity, which makes it kind of boring because it makes the system Hermitian. That's not what we want. So we pick one of the polymatrices, say sigma x. Then it's quite easy to see that if you satisfy the symmetry, that's dx and d naught of this d vector here, they need to be real, whereas the y and z component need to be completely imaginary. In other words, this dot product, dr dot di, is automatically 0, and you're only left with this eigenvalue equation. In other words, for two bands to cross, I now only need to satisfy one constraint, which means that I can find exceptional points in 1D, but also exceptional rings in 2D, as shown in this example here. And this is also why now I'm coming to this parity time symmetry, why you always find exceptional points if you have PT symmetry. So it was realized in this paper, this should be 1997 actually, sorry. In these papers by Bender and Botticher, that if you have a system that has parity time symmetry, that there is a region known as the PT unbroken phase in which all your eigenvalues are real. So when they realized this in the late 90s, this was actually seen as quite a breakthrough or quite a discovery, because it means that you don't necessarily need to be Hermitian to find real eigenvalues. However, you should note that there's also a phase known as the PT broken phase where your eigenvalues become complex. And actually these phases are separated by an exceptional point already in one-dimensional systems. And that's exactly because of this argument up here. The PT already forces this dot product here to disappear. So these symmetry-protected exceptional structures have been seen in experiments. So this is something I already flashed on the second slide. So here in this single interferometry experiment, they realized exceptional rings that we proposed in this PRB paper here. Okay, so far I've talked about something quite simple, namely 2x2 systems with degeneracies.
You provide a bit more information about the experiment.
Okay, now you're asking the theorist about this experiment. So I do not know a lot about it, except that this is sort of, you can think of this a little bit as a quantum walk. So they send in a photon and then it goes around, and then the non-Hermiticity is basically captured in the evolution parameter. So so you have a u e to the I h t, and then this h is the non-Hermitian parameter, and that's how they map the non-Hermitian Hamiltonian in the experiment. But I cannot give you a lot more information than that, I'm afraid. I hope that's okay.
Okay, thank you.
Right, so what now about higher order exceptional points? So exceptional points at which more eigenvectors coalesce and you have a higher degree in the eigenvalue degeneracy. So this is a bit of a technical slide. So I'll try to explain, but I'll also try to be a bit quick about it. So to find an EPN where n is the order of the exceptional point, one can show that one needs to satisfy 2n minus 2 real constraints. So for EP2s, we already saw we have 2 constraints, and every time you increase the order, you need to satisfy 2 more constraints on top. So the way you can see this is if you look at the characteristic polynomial of your non-Hermitian matrix, which you can write in this form, and that's all great, but what it turns out that you can write these coefficients, these sigmas here, in terms of the determinant and the traces of this H. And if you then use the fact that you can set the trace of H to 0, because that is just your identity term, in other words, just a term that shifts around your spectrum but doesn't set the degeneracies, you are left with 2n minus 2 real constraints, namely n minus 1 complex constraints, which gives you 2n minus 2 real constraints. Now, how do we then know that this is actually an exceptional point if I set all these guys to 0? Because it might just be an ordinary degeneracy, right? They can also exist. Another way to think of this is in the following way. So if I take now a Jordan block, which is n-dimensional, and I perform a non-trivial perturbation around this Jordan block, you can write it in this form here with these delta j's. Then this is actually the Frobenius companion matrix of this guy. In other words, if I write the characteristic polynomial of this matrix, it has exactly this form, which means that you can write a relation between these delta j's here and these sigmas here. In other words, these delta j's are exactly the determinants and the traces of this H naught. This also gives some interesting information because I told you before, exceptional points have a square root dispersion. Typically in the field, people say EPNs, they have a 1 over n dispersion, they have an nth root dispersion. However, you can actually show that that's only the case if the determinant of your non-Hermitian matrix is non-zero. If this determinant is 0, regardless of your parameter choices, then you actually do not find nth root dispersion. Okay, so this is some generalities about EPNs and how you can find them. Now, of course, the question is what happens in the presence of symmetries. Then you can make use of the fact that you can write this determinant and the traces in terms of products and sums of the eigenvalues, and then you can use the eigenvalue constraints, the constraints the symmetries put on the eigenvalues to find the following, namely in the presence of these 6 symmetries, you find a reduction in the number of constraints. Instead of 2 minus 2, you find in most cases n minus 1, very much like the pseudo-hermiticity we saw before for the EP2 case. Indeed, that's also in this table here. And in some cases, n. And if you then look at another example, so for example, an EP3 under pseudo-chiral symmetry, you actually find an example like this. The trace of the the determinant of H is always 0 in this case, so you find a square dispersion instead of third root dispersion. Indeed, we see that here. And actually, this symmetry also forces one of the eigenvalues to be 0, so indeed you find the flat bands. Okay.
Could I interrupt?
Yes.
So could
Sorry.
you, so this plot reminds me the dispersion of spin 1 Dirac electrons.
Yeah, that is a very good association, yes.
Does it have any connection? So
actually, that's something a master student is investigating right now. So the big difference is, of course, that for the threefold degeneracies in Hermitian system, this would be a linear dispersion, right? So you have the linear dispersion and then have the flat band intersecting. In this case, this is a square root dispersion. So it behaves differently. And at this point, all the eigenvectors coalesce. So you only have one eigenvector less. So it's definitely a different beast, but it does have similarities, I would say. Yeah.
And on the right subplot, you have 2 points on the diagonals where the all bands touch.
Right. So actually,
what does it mean?
Yeah, very good question. So this is the imaginary part. So actually, it's a bit hard to see in this 3D plot, but it also has the degeneracy in the middle. Otherwise, it wouldn't be a true degeneracy, right? I mean, both the real and imaginary eigenvalues need to be 0 there. Indeed, in the imaginary part, you have another degeneracy here in the corners, which you do not see here. So it's actually not a real degeneracy in the system, because at that point, actually, your system is just fully real. So I guess what you could say is that this choice of Kx and Ky, I mean, this is a 2-dimensional type binding model, if you will, so it's periodic. So at these points for Kx and Ky, I guess, if I remember correctly, the system just becomes Hermitian, because there you just have real eigenvalues. So for this particular choices of K in the Bron zone, you just have a Hermitian system. So the non-Hermitian term goes to 0. That's why the imaginary part in these corners here is 0.
Yeah, I see. Thank you.
Yeah, you're welcome. Okay, so now we found some examples, and I showed you an example without giving you any matrix details of that you can find such high order EPs, but actually it's really tricky to find good examples already for EP3s, let alone EP4s, let alone larger order EPs. Now, one obvious way, however, to generate such higher order EPs is to take a unidirectional Hattano-Nelson model with chain length n. Okay, so what does that mean? So Hattano-Nelson model is the paradigmatic model in non-Hermitian systems. It's a one-dimensional, one-band system with different hopping to the right with respect to the left. And if I now take a unidirectional version, which means I can, for example, only go to the right, then if I take a chain of length n, I very obviously generate a Jordan block of dimension n. I have realized an exceptional point of order n. And this may also remind you of something, because such unidirectional motion in a one-dimensional chain looks very much like the chiral edge state of a Chern insulator. And indeed, there's some correspondence, because you can realize the anomalous boundary physics of a d-dimensional Hermitian system, topological Hermitian system, in the bulk of a d-1 dimensional non-Hermitian system, which is described in this beautiful PRL. And together with a master's student a few years ago, we did a case study. Namely, we looked at a three-dimensional dissipative analog of the four-dimensional quantum Hall effect. So what we did is we showed that in a non-Hermitian three-dimensional Weil semi-metal, you can create a situation where a non-trivial combination of Weil cones survives in the long time limit, namely is in this part, the positive part of the imaginary spectrum, which is the part that survives after time passes. Now that's a small sidestep. If we now actually look at the full Hattano-Nelson model, so I now also lie hopping to the left, you see something interesting. Namely, you get spectral winding. So what you can do is you can write this equation here, which was first introduced in this PRX, which gives you a so-called spectral winding number. So it tells you about the winding of your eigenvalues. And if JR and JL are different from each other, you indeed see, if you look in the spectrum, it looks like this. So you find a ring which winds around some point. And this is has a non-trivial spectral winding number. And this has been associated with what is known as the non-Hermitian skin effect. And what is the non-Hermitian skin effect? It basically means that a macroscopic number of your bulk states pile up on the boundary under open boundary conditions. This here is the extreme case. All states go to the right. This is an exceptional point, so you actually only have one eigenstate and it will just live at the end. If I now also turn on this JL, it won't be exactly on the end, but you'll see that all the states, they want to live on one of the edges. And this is a true signature of non-Hermiticity. Note that one can also see this, if you're familiar with this, I have a work on transfer matrices, where the transfer matrix is in a type binding system, which give you access to bulk states and eigenvalues, etc. And you can show that if this transfer matrix is non-unimodular, so if the absolute value of the determinant of T does not equal 1, then you also have this non-Hermitian skin effect. And this correspondence between a non-trivial spectral winding number and this non-Hermitian skin effect under open boundary conditions was first realized in these papers here. And this introduces a new type of bulk boundary correspondence in these non-Hermitian systems. Okay. Yes.
Could I interrupt you?
Yeah.
Could you remind me this winding number? Does it look the same as the Zag phase for the CCH model?
No, that's a very good question. So the typical winding number for Hermitian systems, you compute it in a very different way, and it says something about the winding of your eigenvectors, if you will. So it says
winding of the wave function.
Yes, exactly. And this says something about the winding of the spectrum. So it's so this is also not well defined in Hermitian systems, because there your eigenvalues can only live on this real axis, right? Yeah. And actually, I will explain this a little bit now, because now the question is, what happens if I now endow this system here with some topology in the Hermitian sense? So I introduce boundary states. And of course, in a one-band system, you cannot have this in Hermitian systems. You need two bands. So what do? We go to the non-Hermitian SSH chain. So I'm going to study the following system now. It's a very simple system. It's 2 bands in the unit cell instead of 1, A and B, shown in red and blue. And inside the unit cell, I've now changed the hopping such that if I go to the right, I hop with T1 minus gamma, and to the left, I hop with T1 plus gamma. So this resembles a little bit this Altano-Nelson model hopping, that the magnitude of the hopping is different. However, between unit cells, I still have a Hermitian hopping T2.
Rory, can I ask a question?
Yes, please go ahead.
So in this model and in the previous one, there is so the going to the left or going to the right is not symmetric. So there is something that, and that's why it's non-Hermitian. But I'm just wondering physically how is it realized? So if I imagine that I have a chain of atom, I don't have this. I need an additional ingredient. So what are these ingredients in general?
Yeah, that's a very good question. And yeah, that's a very good question because I've just thrown them on the slide here. So I will actually show you a few experimental realizations of this chain here in a few minutes. However, I can already tell you, because there I just show the experiments, that if you want to think of this from theory, how to realize this, for example, if you think in terms of the Lindblad master equation, what you can do is you can add an extra dissipator here, which provides an extra channel here for loss, for example, and then you can get these effective non-reciprocal couplings, if you will. So that's one way to do it, but I will also advertise a few examples where they have realized this kind of imbalanced coupling. But indeed, in an atom chain, it would be quite tricky to engineer, I would agree, yeah.
Yep.
Okay, so if I now have this non-Hermitian chain and I look at the spectrum under periodic boundary conditions, I see, and under open, I see the following. Namely, here in gray, you see the spectrum under periodic boundary conditions, and in blue, you see the spectrum under open boundary conditions, with this red band being the zero energy states. You see that the gap closings appear at very different points. So the spectrum is extremely sensitive to boundary conditions, and this was first actually observed in this PRL paper for a related model. Also here, not surprisingly, the bulk states pile up on the boundary, so I have a non-Hermitian skin effect. However, if I look at the biorthogonal product, so if I look at the left and the right of some of these bulk states here in the blue, and I look at the inner product of them, you see bulk state behavior. So, and that's actually because if you look at the left eigenstates, that means you take the dagger of this guy, they are all piled up on the other side. So the exponential overlap really only exists in the middle of the system. That's why they look like bulk states. Moreover, exceptional points, here they are again, with an order scaling the system size appear. So these are these points here.
Or could I interrupt you again? Could you clarify what means pile up? So the probability to find any state is larger at the boundary?
Yes.
So instead of just having plane waves that are uniformly distributed across the system, all states tend to spend large amount of time close to the one boundary.
Yeah.
Okay.
That's exactly it. So you find an exponential localization. Yeah, so indeed the probability, if you will, of finding them will be highest on the boundary. If you look in this picture of the right eigenstates. However, as I mentioned here, if you look in the biorthogonal picture, and this is very much a mathematical trick, they will live in the bulk. But actually, you note here I wrote absolute values. So this, you cannot really think of it as a probability because this can have negative eigenvalues also, or even imaginary eigenvalues. So that's one thing to keep very much in mind, is that this biorthogonal expectation values, right? They don't necessarily give you something that have a very clear interpretation, say, in the physical world. So for eigenvalues, we sort of have a good handle on it because we know you can think of it as lifetimes, and that's also how they appear in experiment. But in this case, it's not so easy to think of it in terms of probability. But one can still compute it and see, okay, you know, we have this overlap in the middle of the system. Yeah. So exceptional points with an order scaling system size appear, and you can really understand this at these points where T1 is equal to plus minus gamma. You can only go in one direction, very much like the unidirectional Hatano-Nelson model I showed, and there you find these EPNs. Moreover, if I now compute the winding number, because this is still Cayley symmetric, then this no longer predicts when the boundary states appear. Okay, so let's now, before I go into more details of the system, very briefly review the Hermitian case and then get back to the non-Hermitian case. So what I've been talking about a few times now is a bulk boundary correspondence, and I've actually used it in two ways. So I talked about the new bulk boundary correspondence. You have a spectral winding number, which gives me a skin effect, but you also still have the Hermitian bulk boundary correspondence, or the conventional bulk boundary correspondence, if you will, which is the guiding principle for Hermitian topological phases of matter. And it has two key properties. Namely, the spectrum under open boundary conditions is equal to the spectrum under periodic boundary conditions plus the boundary spectrum. And a topological invariant exists which predict the number of boundary states. So if we now do the Hermitian SSH chain, so this is now the same chain as before, but I got my zero right. Here's the Bloch Hamiltonian. I will not go into too much detail because I think probably most of you know it, but basically this is what this D vector in this case looks like. Then you can define a non-trivial winding number where this is now different. This is not the spectral winding number, but the winding number of the wave functions. So here you see that this winding number is 1 if this ratio between the hoppings in the system T1 over T2 is smaller than 1, and this corresponds exactly to having 0 energy states in the gap. It's 0 outside of there, so you don't have any states, and this then establishes the bulk boundary correspondence because these 0 energy states correspond to the end states in your system. So my Bloch Hamiltonian has now given me a topological invariant to describe the physics under open boundary conditions. And what I want to advertise now is that one can also get this information using an alternative approach. So we take open boundary conditions from the start, and here I write what representation I then pick for the Hamiltonian matrix, and then we will look for eigenstates of the following form. So these red and blue circles correspond to the A and B sublattices, and what I write inside are the amplitudes of the eigenstate I'm looking for, which you can write in this way, but more compactly in this form. So here N is the normalization, M here labels the unit cell, and you can see here this only has a non-zero weight on the A sublattices. And it goes with this vector of R. This actually turns out to be an exact solution, and one can find that in the following way. So by making use of the local destructive interference on B, which gives me the zeros here, I can basically write this wave function. I assume I have 3 sides. I apply the Hamiltonian, and then I see that as long as R satisfies this equation here, this is an exact solution. Namely, R needs to be the ratio of T1 over T2. And this is an exact solution for a system with a broken unit cell, so here with 3 sides, and it's an approximately good solution for a chain with an unbroken unit cell. So if I start with red and end with blue, so I have A on one end and B on the other boundary, as long as this ratio is smaller than 1, so as long as the state is localized to the boundary on the left. And this I described in one of these papers here, and it turns out that this kind of way of writing exact solutions goes well beyond even non-Hermitian, but well beyond SSH chains. So you can do it in higher dimensions, also with higher codimensions, etc., which is described in these works here. So what does this then tell us? This is, eigenstate here with this ratio basically says, okay, you know, this is well localized if T1 over T2 is smaller than 1. And indeed, I find 2 eigenmodes in that case. So this is exactly what the winding number also told us. I don't find any end modes when this ratio is larger than 1. And the end modes need to gap out when this ratio is 1. And I mean, when this ratio is 1, you can see that this is equally localized in each of the unit cells. So it has to be bulk state. Up to finite size corrections, of course. So this is an alternative way to actually understand in full when do I have these boundary states. And we're going to use a similar approach for non-Hermitian systems. So here we again have the non-Hermitian SSH chain. And I talked about the bulk boundary correspondence, which has 2 ingredients. The spectrum needs to be the same. Well, we clearly see that that's not the case. The topological invariant needs to predict the boundary behavior. That's also not the case. So we have an breakdown of the conventional bulk boundary correspondence. And we need to now remedy this situation. And you can probably already expect that I will use this method that I showed before for finding exact eigenstates to understand what's going on here. So we will remedy the situation. However, before I go into that approach, I want to advertise that there's also another approach to do this. So I call it here approach 1. You have what is known as the non-Bloch bulk boundary correspondence. Very mathematical. The idea is that K now becomes complex, and then you can define a generalized Bloch Hamiltonian, which then accurately predicts the physics of your system. So you can now make K complex, where you then need to find what this R is, which is not so easy to do. So in 1D, it's well known. In higher dimensions, it's not quite well known how to go there. But if you then go through this machinery, you can find a generalized Bloch Hamiltonian, which then allows you to derive, to properly find the topological numbers of your system, invariance. However, I want to talk more about the second approach, because this is the approach that we worked on, which is the barorthogonal bulk boundary correspondence, where we will explicitly use a barorthogonal expectation values. So here's the non-Hermitian SSH chain, where I'll show you exactly how this works, but this can also be generalized. And we look for eigenstates of the following form. Now, this looks almost the same as what I wrote for the Hermitian SSH chain. However, you see now that I have this minus gamma up here because of the fact that I hop now to the left of T1 minus gamma. You can also find a right eigenstate, which looks, a left eigenstate, which looks almost the same, except it has plus gamma, which is exactly because the left eigenstate of H is the right eigenstate of H dagger, which in this case basically amounts to flipping the sign in gamma. And these are inequivalent, as we know happens for non-Hermitian systems. And of course, they become equivalent and identical to the Hermitian SSH solution if gamma is 0. We now use this to define a so-called barorthogonal polarization. So this is how it's defined. So let me take you through what this means. So here, what I'm doing, I'm taking the sum over M, where M is these unit cells. I put M here also as a weight. Then here you have an operator, which is the projection operator onto the sublattices A and B in the unit cell M. I divide by the total number of unit cells, and then I take the barorthogonal inner product with expectation value, with respect to this psi r and this psi l. Then I send M to infinity and to compute what this P is. So let's see how that works. You can, when you plug in these exact solutions here, you can convince yourselves that if RL, RR is larger than 1, that this P goes to 0. And this corresponds exactly to the regions here where I do not have a 0 energy state. If RL, RR is smaller than 1, P is 1, and I have 0 energy boundary states. And P jumps when RL, RR is 1. And this intuition is very similar to the Hermitian case, where I said, okay, you need to now look at whether this ratio T1 over T2, which would translate to one of these R's, is smaller or larger than 1. Here, the combination of right and left actually gives you the correct information. If I were to just look at RR or RL separately, I would predict gap closings in the gray spectrum, not in the blue spectrum. And we know that we call this a barorthogonal bulk boundary correspondence, because the barorthogonality of the system under OBC gives us exactly the information as to when bulk states appear and when boundary states appear. So what about these skin states? So why, I mean,
Could I interrupt you?
Yes, please go ahead.
Could you also comment why it's called polarization?
Yeah, this is this is a method that we developed still in my PhD. We call it polarization because it has a bit of the same kind of flavor as the polarization that one sees in Hermitian systems. But yeah, that's the only reason. Because it looks a bit similar.
Even if the system were normal, I mean, were Hermitian, would it define just usual electrical polarization?
No, it would actually correspond exactly to what you would find using the winding number. So there are some works where they have connected polarization also to topology. So it sits more in that. But basically, if you set gamma to 0 here, you'll actually find this RL and RR, they're equal. So you would find the absolute value of R. So this basically would reduce to what you would find for Hermitian systems in terms of winding numbers. So this gives you this works in Hermitian systems as well, if you will. You just don't really need to do this because the normal bulk boundary correspondence holds. But
okay, thank you.
Right, so I talked about the fact that if you have a spectral winding number, you have a skin effect. And that actually tells you that you will have a broken bulk boundary correspondence. So it's really the skin states that give you this interesting physics. So let's investigate this a little bit further, namely, how sensitive is the system actually to boundary conditions? So I have an open chain, I couple it with some term gamma, and then I start increasing the value of this gamma to see when do I lose this interesting physics. And this actually happens already at exponentially small values with the system size. So this is some crossover gamma. It's not a critical point or anything, but if you start to couple, and at a very small exponential coupling, you'll see that the skin states can start tunneling through, and you actually recover physics that you would expect from PBC. So you would go to a case which looks much more like you would think were to happen if you go from PBC to OBC. However, that doesn't mean that you cannot still see this interesting physics that I just described. Because of locality constraints in physical systems, you will actually still be able to see the system really under open boundary conditions, as in this kind of coupling will be suppressed, which was shown in this work here. If you now instead consider domain walls, you can also still see the same physics. So if I couple my non-Hermitian SSH chain to a Hermitian SSH chain, which is in the topologically trivial phase, and I vary the gap in that system, you'll see the following. So if this has a very large gap, you'll have a spectrum like this, where you still see zero energy states appearing in the same regions as before. So you still have this physics that you get also under pure OBC. If you now start to close the gap, at some point you see the zero states, they disappear, the gap closings, they also start moving, and in a fully gapless case, you see the gap closings sit at these black dashed lines, which indicate the points where gap closings appear under periodic boundary conditions. So basically what happens is, by varying this bulk gap, at some point, these skin states can start tunneling through, and you again recover the physics you would expect from PBC. Now, finally, here comes some experimental realizations that I advertised. These are mostly in classical systems, though. So in quantum systems, as I said, you could do something like with having a Limblad system where you then couple the sides to dissipate, or you have some non-local dissipation. Then you can also effectively get this kind of descriptions out. But this has not yet been done in experiment, to my knowledge. So one platform where you can, or where this chain has exactly been realized, is in topoelectric circuits. There you can use amplifiers and resistors to get this different couplings between sites. And here in the voltage profiles, they exactly see also this skin effect behavior. Another system is in active mechanical metamaterials. Here they didn't quite realize the same system, but another system with these couplings. Yes, please.
Could you explain in more details why for this contour coupling to the right and to the left, they're not the same?
Sorry, what do you mean exactly?
These models have the hopping amplitude to the right and to the left.
Yeah.
They're not the same.
No.
How the situation is achieved in this kind of systems?
You mean, for example, in this electrical circuit? Or yeah, so here you can see the schematic details of how they realize the coupling between A and B. So you have some resistors, some capacitors. So this is quite a complicated setup, but basically it has the effective effect that it looks like this. And the way you can think of this is that the physics in electric circuit is governed by Kirchhoff's law. So what comes in to the node has to come out, right? So you can write the so-called Laplacian matrix, and this you can think of as a non-Hermitian matrix. So then this effectively realizes this non-Hermitian Hamiltonian, and then the eigenstates of that are the voltage profiles. So if you then send in the current and then you measure, then you can find these different profiles depending on how they set the parameters, and you find either localization on the left or on the right. So,
why is it that some effective something hops from A to B more efficient than from B to A? Isn't some time reversal symmetry is supposed to be broken within each side?
Yes. So that is, they have engineered it in this way, in this setup.
Okay, thank you.
Maybe it is in the link between the sites that there is something going on.
Yeah. Yes, it has to do with how A and B and how these two nodes are connected. So basically, the current prefers to go more in one direction than in the other.
Okay.
Yeah, and you can also get this sort of non-reciprocal couplings in mechanical systems with robotics. So there they can introduce basically some form of resistivity also in the couplings. And you can also see the non-unitary quantum walks. So this is very similar also to the single photon interferometry experiment, where you have a time evolution governed by a non-Hermitian matrix, so you get some lifetimes. And here, if you can see that in this quantum walk setup, every time you go to the next step, that the probability of being on the edge is higher than in the bulk. So this is also a form of a non-Hermitian skin effect. Right, so this method I talked about, this orthogonal bulk boundary correspondence, can be generalized to higher dimensions. So you can do it in 2D, for example. So this non-Hermitian Chern insulator example I already had on my very first slide, where you can now make use of this condition here to write a phase diagram, as I show here. So this is this example. You can also do it in higher order topological models to systems where you have corner states or hinge states. You can also make use of these biorthogonal properties to fully understand when these kinds of states appear and where they exist. And you can also go to multiple boundary states. So if I have more than one, say I have 2 or 3 or whatever, I can also find such a generalized biorthogonal polarization. Right, so how am I doing on time, actually?
Very good.
Okay.
50 minutes.
Okay, so I still have a bit of time. Okay, then I'll briefly touch upon something else.
We would happy to continue if needed.
Okay, no, but actually,
don't worry
let me then. No, but actually, let me then go quickly over these 2 slides that I have. I wasn't sure if I would have time or not, and then I go to the conclusions. So let's change text a little bit. So far I've been talking about exceptional points. I've been talking about the consequences of having these higher order exceptional points in open systems. I've talked about a new type of bulk boundary correspondence, actually 2 new types, if you will, that you can find there. What about if we instead to think of a non-Hermitian system as a bath? So what happens to the dynamics of a quantum emitter when you couple it to such a non-Hermitian system? And here you see an example of a photonic chain, which has a unidirectional coupling. So this is the unidirectional Hatano-Nelson model we had before, which is lossy. And I couple a quantum emitter. So this is captured, we assume this is a theory work. We assume this is captured by the Limblad-Master equation. So this is this Hamiltonian of the quantum emitter. This is the Hamiltonian of the chain, and this is the interaction between the two. Then you can actually find an exact solution for this, to the evolution of this density matrix in the single excitation sector, which in terms of this effective Hamiltonian. So you can show that if you only assume a single excitation, that the bath is exactly described by a non-Hermitian effective Hamiltonian. So you can ignore the jump terms, or sorry, the recycling terms. So then you can start playing games and see, okay, how does this non-Hermitian effective bath then affect the dynamics in my system? So if we indeed look at the unidirectional Hatano-Nelson model, we see the photon spectrum forms a loop. This we already know from the example I showed before. Then you can get different kinds of bound states. So you have, if your energies is then inside this loop, you have skin mode-like bound states. So they decay in a direction that you would not expect. Whereas you have Hermitian-like bound states, so sort of what we know from Hermitian systems, if the energy is outside of this loop. Moreover, if you look at photon dynamics, you would see amplification, for example. So these are things that one would not expect from Hermitian systems. If I now look at a different example, for example, a system with PT symmetry or passive PT symmetry, so because this is an effective Hamiltonian coming from the Limblad equation, actually my imaginary energies always need to be negative, which means I have what is known as passive PT, which basically pushes my spectrum in the negative imaginary plane. This has an exceptional point. Then you find, for example, algebraic decay for the emitters. And if you're interested in this kind of idea, then we have many more examples of the effects of different kinds of hermiticities on the emitter dynamics in this paper here. So with that, I would like to conclude. So I hope I've convinced you that non-Hermitian topology is extremely fascinating. I showed you several examples, Fermi arcs, exceptional points, bulk boundary correspondence, and also non-dissipative analogs of Hermitian boundary physics. Here's again the review paper that I mentioned already in the beginning. So I'd like to thank all my collaborators on the several projects that I've done in this field. Here is a photo of my group. As you can see, I need to take a new photo. So I was joined by a new PhD student very recently. If you're interested, here is the URL to my website. And actually, I'm looking for postdocs and PhD students. So if you have any candidates, then please send them my way. I thank you for your attention.
Thank you for fantastic talk. Do we have any questions? Pablo, please just go ahead.
Yeah, thank you. Thanks so much for the talk. It's very interesting. So I just wanted to ask, what is in the slide number 21? You're speaking about this R term. Well, this R that goes to different powers. Do you know what?
This one, you mean?
Yes,
Yeah.
the R one. What is physically what it represents in general? In other
Right.
systems?
Yeah. Thank you for your question. So basically what you can see from this equation is that depending on whether this R is larger or smaller than 1, you get exponential localization. So if this R is smaller than 1, you'll see that every time I go to the next unit cell, my localization, it comes with an extra power of m, so the localization drops further. So this is exponentially localized to the left when this R is smaller than 1. And actually, and this is also why we say it's exact for a broken unit cell. If this R is larger than 1 in a system with a broken unit cell, you'll see that it just localizes on the other end, exponentially localizes. So that's what this R basically tells you. It's the localization parameter, and you can actually make a connection directly with the localization length of this state via taking the log 1 over. Yeah. So, and that's also why if this R is 1 or if it's a phase, right? So if the absolute value of R is 1, you see that the localization is the same in each unit cell. So then it has to be a bulk state. So this is exact for systems with a broken unit cell. And this also tells you something interesting that people don't usually think about. But if you take an SSH chain with an odd number of sites, you always have a zero energy state, and it's either on the left or on the right. And it's captured by this guy. But if I now reintroduce the site at the end, right, then this becomes not exact, but approximate, but it's a very good approximation. So especially if the chain is long, the localization is very good to the left, it won't fill the other ends. This is what the state will look like. And then you can write actually a similar solution that exists on the B sublattices on the other side. So this chirality that is in there, that it only exists on the A sublattices, you actually still see that under OBC up to finite size correction. So it will have very small weights actually on the B sides. Yeah. Does that explain your?
Yeah, thanks so much for that. And just another quick question, sorry. What happens with the edge states? Are still existing in the existence of high order exceptional points? Sorry.
Yes. Yeah, actually that's let me bring this up, this figure here. So you see indeed here you have the zero energy states, and here you have these high order EPs. So it still exists, but it's indeed a bit weird. So if you look at the exact solution here, so I set these higher order EPs, right? Here's the spectrum. They appear when T1 is plus or minus gamma, so you can only go in one direction. They actually see that you get zeros in the top of one of these guys. But if I remember correctly, the normalization factor somehow takes care of that. So yeah, they still exist. Yeah.
Thanks so much.
Yeah.
Any other questions? Please just go ahead.
Hi, I was wondering whether I can ask, on this slide actually, when you said that the bi-orthogonal polarization can be used to indicate topology, I'm just wondering whether you can elaborate on that. Thanks.
Right. So thank you for the question. So basically what we show here is that you can use these exact solutions to exactly understand when you have the boundary state. And of course that makes sense because as I'm saying, they should actually describe boundary states. And this is one vehicle with which we do this, which gives you out these relations, this RL-RR, but that's actually what I'm after, getting this RL-RR, which is very similar to what we saw for Hermitian systems, where this R that I just talked about for the SSH chain, the Hermitian SSH chain, gives you information as to when the boundary states exist or not. Now, to connect this to topology, this tells you when do I have a boundary state. Now, one can never be 100% sure whether this is actually a topological boundary state. So one can think of this as a topological invariant in the OBC case, because most you know, you have to have some sort of other type of defect if you're going to have a boundary state. So typically this is going to be a topological state, but one definitely has to be sure that this is topological, which in this case is a bit hard because it's non-Hermitian. However, we know here it inherits basically that kind of topological charge from the Hermitian system. But basically this tells you, do I have boundary state or not? Does that explain a bit better?
Yeah, I think I might have misheard that. I thought there was a
Okay.
topological invariant associated with P, but that's not
Yeah,
really.
yeah, it's a bit, I find it a bit too strong to call it topological invariant. It's
Okay,
actually
yeah.
reason.
Okay, thank you.
Yeah.
Yeah.
Any other questions? Please just go ahead and ask.
I have a comment or a question, maybe. Yeah, okay, I don't know if it's very, okay, maybe it's, okay. I would like to know what you think about that, or if you have any, if you can answer this. So for emission system, I think it is now, so we have this edge states physics, and recently, or not so long ago, at least it has been understood that in fact it is, so we don't need to have quantum mechanics, and it's in fact even realized in nature. So I'm not sure if you are aware, but there is this paper in which some authors have understood that there are some equatorial waves on Earth, which are chiral and which can be interpreted in terms of topology in the Hermitian case. And so I'm just wondering, it seems that this non-Hermitian physics and non-Hermitian topology is very generic. So do you have any, I'm wondering if it's also, do you think it's realized somewhere in nature? Not in artificial system, but like, are there any analogous system to this chiral equatorial waves in this non-Hermitian case? Or?
Yeah, that's a very nice question. So I know the paper you mean. It's actually, I think, by Pierre de Place, right? And some others. I cite them because they also did some work on higher order EPs. Yeah, so they found the Chern numbers too, right? For these waves. Actually, I don't know such a nice analogy in that form. I do know that some people like to sort of make this kind of thought, and I kind of like this thought, but it's very much a mind game, is that in a way, of course, we always assume systems have to be Hermitian and the full system is Hermitian. And actually, we could think of the whole universe as being Hermitian, except that we have black holes, so we lose information. So in that sense, you could even sort of think as, in the end, everything is non-Hermitian because of that. It's a kind of a cute way to think about it. I don't know something so nice as what you were saying right now. Oh, this is because there, of course, very nicely the topology appears in nature. I would say we are still looking, because I do think the non-Hermiticity is more than just effective way of thinking about things. I definitely think there's something more fundamental here, but I don't really know of any nice example like you just mentioned for Hermitian topological systems. But I quite like the thought, so I will think on this more. Yeah, thank you.
Okay, thanks.
Thank you. Do we have any other questions? Please just go ahead. Let me ask the question. For Hermitian case, the key concepts are Berry connection and Berry curvature.
Yeah.
Do they make sense here? Can they be generalized and helpful for this kind of systems?
Yeah, that's actually oh wait, let me just get the right slide. Here. Yeah, that's something I did not mention, but indeed they can. So one way to connect sort of the traditional way of thinking of topological invariance in the PBC case to the OBC case is actually via this method here. So this connects very much to the way we usually think about it, where you have to redefine your K to find this generalized Bloch Hamiltonian. Now, here's some methods where you can machine learn how to do this in 1D. Actually, I very recently saw a talk by one of this author on how to do this for higher dimensional systems, but this is still very much in the works. So it's not quite well understood yet. But basically, this then allows you to define topological invariance. Now, how do you then define the topological invariant? Because you have a left and a right eigenstate. So in terms of the Berry curvature that you talked about, it has been shown that you can compute it, of course, using right, left, or left, right, all of these combinations, and the Berry curvature is actually different depending on this choice. However, what they showed in the paper, it's called I think it's non-block Hermitian topology. I can look up the reference for you if you like and email it to you. But basically what they showed then is if you compute the Chern number, that regardless of these different Berry curvatures, you still find the same value. So you can still make such computations. And for example, in this paper here, they did this for the non-Hermitian SSH chain that I'm also studying. There they find some generalized version for the winding number, also using left and right states. So there are definitely generalizations that one can do, but it's not always so obvious what is the best choice, because you have more choices. So one has to really check and be careful about this. Yeah.
Okay, thank you. Do we have any other questions? Please just go ahead and ask. If not, let's thank the speaker again.
Yes, thank you also.
Thank you for fantastic talk. So in this case, bye everyone. See you in a month.
Bye-bye, thank you.
Have a nice day.
Same to you. Bye-bye.